Hi, this is Math 8, Unit 5, Lesson 9 on linear models. We're going to model situations with linear functions. So the first one, you have a statement here that says candlelight. It says that a candle is burning and it starts out 12 inches long after 1 hour and it is 10 inches long after 3 hours. After 1 hour it's 10 inches long, after 3 hours it's 5.5 inches long. All right, sorry, I was getting my little iPad out here to see if I can get our little applet opened up, ready to go. Let's see if I can get this working here real quick. All right, so it says, when do you think the candle will burn out completely? And so you might be using in your class today a little thing like this. Maybe you use your iPad or computer and you can graph this out if you wanted to do that there. And you can use a tool then to kind of plot some points for the candle that could work. And so there's a variety of ways to do that there, but that's for you to play at. You can also just do the math here, which is what I'm going to do just with paper pencil. All right, so when do you think it's going to burn out? So really this is kind of your warm-up question of the day. It says it starts off 12 inches and after 1 hour it's down to 10. So we see that in an hour we're dropping 2 inches per each hour, right? After 3 hours, it's 5.5 inches long. So we can think that after 1 hour, well, at the starting point, we're at 12, right? And at 1, we're down to 10. At 2, we're not sure. But at 3, we're down to 5.5. So if we were dropping 2 per hour, that would be 8, and that would be 6. And so this would be about 4, something like that, if we were doing 2 per hour. So at 4, we have 4 inches left. At 5, you're down to about 2 inches left. And at 6, you're down to nothing. So if I was dropping 2 inches per hour, if that was a constant rate, I would say it would burn out somewhere between 5 and 6 hours after lighting it. Okay? Is the height of the candle a function of time? That means, does the height of the candle depend upon how long it's been burning? We would certainly in this case say yes, right? The longer I burn the candle, the more it changes, or the change in the height that's going to be present. I'm going to have the height that's going to be dependent upon how long the candle has been lit. If I have it only lit for 2 hours, I have an 8-inch candle. If I have it lit for 5, I have a 2-inch candle. So yes, the height is a function of time, right? Because height depends on the time it's been lit. So if yes, is it a linear function? Linear means it's going to be in a straight line. If I plot these points, I would have a straight line. Well, we can already tell that if it was a straight line at 2 inches, that means if it was 2 inches per minute, right, it would look like a straight line. This one here, based upon this data point there at 3 at 5.5, it's hard to say that it would be a straight line because it's already varied a little bit there. It's close to a straight line, but not exact. So if you wanted to say it was a straight line, you could say it's pretty close. If you graphed it, there might be a little variance, right? You know, it might kind of like move down a little bit, but that's not a major concern. It's clearly not super straight, but it's close. So we would say it's close. All right. So in this case here, is it a linear function? We would say it's pretty close to linear. All right, let's look at the shadow one, number 2. It says when the sun was directly overhead, the stick right here had no shadow. So that's our stick, hard to see in my picture here, sorry, but there's no shadow. After 20 minutes, the shadow was 10.5 centimeters long. So this is our shadow right here at 10.5 centimeters long, and it got to that length, it said after what? After 20 minutes. Here, we see that after 60 minutes, we have a shadow that is 26 meters long. So here we have 0 shadow, 0 meters. Here 10.5 centimeters after 20 minutes and 26 centimeters after 60 minutes. Based on this information, estimate how long it will be after 95 minutes. Well, to figure out how long it will be after 95 minutes, go back to what we've been doing before. You have basically a rate, right? rate, and we multiply that by, in this case here, our time, or our x value, or our independent value. So, do we have any rates in these pictures here? We do somewhat. There may be a little different between the two of them, but we could use this first rate as an example and say, well, it has a rate of about 10.5 centimeters every 20 minutes. Now, we know that's not perfect because in 60, if I was to go from 20 to 60, that's a times 3. Well, 10.5 times 3 is going to be more than 30. So this rate already is not as constant as we would like it to be. But for now, let's use this rate, 10.5 centimeters every 20 minutes, and multiply that for 95 minutes. If I multiply 10.5 divided by 20 times 95, I end up with 49.88. Or I could say that's about 50 centimeters. So after 95 minutes, I should have something that's about 50 centimeters long. Is that accurate? Hard to say. This is again just an estimate based upon this one rate that's given right there. Number 2 does say that after 95 minutes, the shadow measured 38.5 centimeters. How does this compare to your estimate? Well, my estimate was too long, right? I had 50 and it ended up being only 38.5. And so it was about 11, in this case here, we would say 11.5 centimeters too long was my estimate. I was off there. It happens, hey. Question number 3. Is the length of the shadow a function of time? So does the shadow length depend upon how long it's been since we started? Okay. And we would say, yeah, the shadow length is a function of time. Yes, it is, because the shadow length depends on the time from when you started. The question next is it linear? Does it go in a straight line? And in our case here, we would say, no, it's not linear in the terms of like being a straight line for us to say, yep, it's definitely like a smooth straight line, because our points are different. I mean, if you just plotted this out, you start off with 0, 0 right there, and then if you move to our time is our, so here's our length, sorry, and here's our time, and right, if we had 20 minutes here, 40 and 60, and then we ended up actually with 80 and 100, so here's 95, right? We had at 20 minutes, we were at, let's just go here, we'll go with 10, 20, 30, just for fun. At, I should label this 20, 40, 60, 80, 100 minutes. So at 20 minutes, we were a little bit above 10, right? At 60, we were like at 26. At 95, which is somewhere about here, it said we were at 38.5, so somewhere up here, right? If I start at 0, here's what my graph looks like. Something like that. Again, just an approximate graph. Would you describe this as linear? We'd probably say, nah, not very linear. And that's probably why. We just don't have points that line up in a line for us. In activity 3, we go back to our activity on recycling. It says in an earlier lesson, we saw this graph that shows the percentage of all garbage in the U.S. that was recycled from 1991 to 2013. It says sketch a linear function that models the change in percentages, percentage of garbage that was recycled between 1991 and 95. So we're going to take a point 91 and 95, and we're going to draw a line like this, right? And that would be a linear function from 1991 to 95 there. So for which years is the model good at predicting the percentage of garbage that is produced? For which years is it not so good? Well, based upon this model, I could say it's good for 1991 to 1995. seems to work great for that, but it's pretty much bad for all other dates, right? These dates here have nothing to do with that line. They're not even close. It doesn't work for those at all. So it's a linear function, a nice model, but it only works for some points on the graph, not the others. Number 2 says, well, pick another time period to model with a sketch and sketch linear function. For which years is it a good model? So for my next sketch, I thought, well, let me pick something kind of close. I went with 1998 to 2011. So this is 6, 7, 8. I went from here to 2011, which is here. So if I drew this as a linear function, there, well, the reason I picked those 2 points is I have something that seems to be almost like a line from there to there. Granted, it obviously curves, but in this case here, it would be good for just those dates really, but it's going to be bad for things before 1998 and after 2011, right? I just picked 2 points where it seemed to work pretty good, but after that, it doesn't work very well, and before that, it really doesn't work too well either. So again, just one little model there. You could pick your own dates, that's up to you. And so a summary for today's lesson, because today was pretty quick here, we say that what we have is we have some equations here, and these equations are examples of a mathematical model. Okay, a mathematical model is a mathematical object like an equation, a function, or a geometric figure that we use to represent a real life situation. Sometimes situation can be modeled by a linear function. We have to use judgment what is a reasonable thing to do based on the information we are given. So the models we had in our previous little activities were based upon real life situation, whether it be recycling or whatever that might be, a shadow. Those are real life situations that we model with a graph, and we can turn that into an equation, but it needs to be reasonable in order to actually work out. All right, let's take a moment now to work on tonight's homework. So if you can start that, it'd be great, and then we'll check it together here in just a second. All right, tonight's homework, Unit 5, Lesson 9. It says on the first day of after the new moon, 2% of the moon's surface is illuminated. On the second day, 6% is illuminated. All right, so from day 1 to day 2, we seem to be increasing by about 4%, right? Plus 4% from one to the next. Based on this information, predict the day on which the moon's surface is 50% illuminated. All right, so a couple ways of doing this here. I can make an equation, or I could just do some some longer math here. Depends how you want to look at it, right? We know that we start at day 1, we're at 2%, right? 2%, and at day 2, we're at 6%. So I want to continue this going up by 4%. So I'm going to just go 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. If I go by 4%, I have 6, 10, 14, 18, 22, 26, 30, 34, 38, 42, 46, and then 50. So on day 13, if I just go up by 4% each day, I should be at about day 13. Okay, so at day 13 equals 50% illuminated, right? And so if we double that, we would say day 26 would be 100% illuminated. That's what we would say. B says the moon's surface is 100% illuminated on day 14. Does that agree with our prediction? Based upon a 4% per day, we said day 26, not 14. So we would say, nope, it sure does not. It doesn't seem to work that way, does it? So is the percentage illumination of the moon's surface a linear function of the day? Linear means it's just a straight line based upon how long you've gone on or what day of the month you're in. Linear would be a simple 4% change every single day. That's a linear function. If we graph these points out, we would get a straight line like such. But because we have 100% on day 14, that's not going to quite work, is it? We're going to have a graph that looks much more like this, a curve of some sort. So we would say this is not a function or not a linear function. Okay? So it's not a linear function of the day. Number 2, in science class, Jada uses a graduated cylinder with water in it to measure the volume of some marbles. After dropping 4 marbles, so they are all underwater, the water in the cylinder is at a height of 10 milliliters. After dropping 6 marbles, the height is 11. Okay? So we have a little cylinder, right, of some sort, and when you put 4 marbles in, then the water is going to be at 10. But if I put 1, 2, 3, 4, 5, 6 marbles in, then the water is going to be at 11. Alright, so we have an increase there. When I had 4, I was at 10 liters, or milliliters, and when I'm at 6, I go up to 11. So I can see that by adding 2 marbles, that increased by 1 milliliter, didn't it? So how much does 1 marble increase? If 2 made me go up to 1, then we would say that 1 has a volume of half of that. So 0.5. So the volume of 1 marble is going to be 0.5 milliliters. Okay, so get that right there. So that's going to be our volume of 1. Yep, volume of 1. So ml would be our abbreviation, not mil. Sorry about that. So 0.5, because that's half. If 2 give you 1 full milliliter, then 1 is going to be half of that. How much water was in the cylinder before any marbles were dropped in? Well, when we had 4 marbles times 0.5, that's their volume, we know that that is going to be how much that's going to be. That's going to be 2, right? So we have 2 milliliters of space taken up by 4 marbles. So that's what's in there. I know that I had 10 milliliters with them, so if I take the 4 marbles out, so 10, my volume of water there, and I subtract the 2 milliliters of marbles, which is 4 marbles, that gives me 8. So I started with 8 milliliters of water to start with. That's what I began with. What would the height of the water be after 13 marbles dropped in? Well, to do that, we take what our starting point is, 8, and we're going to add to it the volume of 1 marble times the number of marbles I'm going to put in, which is 13, right? My starting point of water, 8, plus 1 volume of a marble times the number of marbles. Well, 13 times 0.5 is going to be equal to 6.5, so I end up with 8 plus 6.5, which equals 14.5, would be the height of the water after 13 marbles are dropped in. That's where we would be. Is the volume of water a linear relationship with the number of marbles dropped in the graduated cylinder? If so, what does the slope of the line mean? If not, explain your reasoning. We would say in this case here that yes, this is a linear relationship, and the reason we know that is that because it works like this. Y equals, or our volume of the graduated cylinder is going to be equal to the volume of one marble times the number of marbles plus my starting point for water, like so. So my slope of the line is going to be, in this case, slope is the volume of one marble. And that's what my 0.5 represents there. Number 3, we have a couple of equations to solve here. So to solve these, we're going to go ahead and, on this one here, let's do some distribution. So 2 times 3x is 6x. 2 times 2 is plus 4. We make that equal to 2x plus 28. If I want to get the x's on one side and the whole numbers on the other, I'm going to subtract 2x, so I have 4x over here. And if I subtract 4, I subtract 4. So 4x equals 24. And to solve for x, I divide both sides by 4. So I find out that x equals 6. For this first one right there, x equals 6. Next one here, let's put things on the same side, right? So let's do add 3y, that's going to be 5y. And over here, let's subtract 13. So 5y equals a negative 56. We're going to divide all of that. Oh, why did I put 5 there? Sorry, that should be 8y. Sorry. 5 plus 3 is 8y. Sorry about that. So now for here, I'm going to divide both sides by 8. So that y equals negative 56 divided by 8, which is negative 7. And finally, our last one right here for this front page. Is there more? Yeah, it's on the page. For this front page, we do 4 times 2a is 8a, and then 4 plus 2 is plus 8. That's going to equal 8 times 2, which is 16, and 8 times a negative 3 is negative 24a. Combine our like terms, so let us go ahead and add 24a, because I like to work with positive variables if I can. This is me, preference, so this becomes 32a. I'm going to subtract 8, it's going to equal 8. And I want to get the a by itself, so I divide both sides by 32. So that a equals 8 divided by 32, which is 1/4. Because 8 times 4 is 32. So a equals 1/4, and we're done with that part. Let's turn the page and look at number 4. It says, for a certain city, the high temperatures in degrees Celsius are plotted against the number of days. So we can see that we have some points here that are plotted on our graph. We have a point there, a point there, and a point there. Okay? And so what's taking place here, if we were to kind of map this out, is it looks like that over the course of 2 days we're going to go up 1, 2, 3, 4, and over 2. So we're really going up about 2 every day. That's the pattern there if this was to continue. Up 2 over 1, up 2 over 1, up 2 over 1, up 2 over 1, 2, 1, 2, 1, and there we are. So that's what the pattern looks like in terms of the graph that we are given. It would look something like this. So those are our high temperatures over the course of a few days. Based on this information, is the high temperature in the city a linear function of the number of days? So is the temperature here a linear function of the number of days? So days is here, temperature is there. Is that linear? We would say, in this case here, yes, it is, right? And that's because each day increases by 2 degrees. Okay? And that's what we would say based upon the graph. But the reality is that it can't go on forever. Could you imagine if it just kept going up 2 degrees Celsius every day? At some point, you're going to be pretty hot and the temperatures are going to start to cool down. The season's going to change. You'd be in a bad situation if the temperature continued to go up 2 degrees Celsius every day for the rest of your life. Okay, so there's a maximum temperature it could reach. So yeah, the graph shows a linear function, no problem, but the reality is that at some point this temperature has to come back down and cool. Just not what we've shown there. And finally, the school designed their vegetable garden to have a perimeter of 32 feet with length measuring 2 feet more than twice the width. Using L to represent the length of the garden and W to represent the width, write and solve a system of equations that describes the situation. Sure. Alright, well first of all, we know that a perimeter is 32. Now to find a perimeter, that's going to be 2 times the length plus 2 times the width. That's just the given formula for the perimeter. We're also told that, what? That the length is 2 feet more than twice the width. So we know that the length equals 2 feet more than twice the width. All right, and you can write 2w plus 2. So twice the width plus 2 tells you the length. Now to do a system of equations, I want to take one of these and plug it into the other one. So I'm going to take my value of L right here and plug it into that space right there. So I have 32 equals 2 times 2 plus 2w plus 2w. We've just substituted this L value for the L right there. Now we'll distribute and we'll say 32 equals 4 plus 4w plus 2w. We're going to combine some terms here. So let's subtract 4. So we have 28 on this side equals 6w. 4 plus 2 is 6w on that side. I want to get the w by itself, so I'll divide both sides by 6. And 28 divided by 6 is 14 over 3. Or I could also write that as 4 and 2/3. So my width is going to be 4 and 2/3. Do I know my length yet? Nope. I'd have to plug this number back in over here. So I can plug it into this one, which is just fine. I could say that my length is equal to 2 plus 2 times, and I'm going to use the fraction, okay? I'm going to use 14/3, so 14 over 3. So that becomes 2 plus 28 over 3. And again, this can be changed, 28 over 3. Depends on how you want to write that there. That 28, 3 goes into 28, goes in there 9 times with 1/3 left over. So I have 2 plus 9 and 1/3, which is going to be 11 and 1/3. So my length is that, my width is that. So in terms of my dimensions are going to be, you always write the width first, so 4 and 2/3 by 11 and 1/3. Those are my dimensions for my garden. That's my width and my length. Alright, and that looks like it's it for today, and we'll see you next time.